Hey everyone, it's Ken. In this video, I want to introduce a topic that doesn't seem like it's very well tied into anything we've done before, but it is hinting at or foreshadowing what we're going to do in later sections, namely integration. So the problem that I'm going to try to confront in this video is how do you calculate the area of something? So for simple shapes, you know, like the area of a rectangle is base times height, the area of a circle is pi r squared, and so on and so forth. But it's kind of funny, you may not have thought, or at least I hadn't thought very carefully when I first took the class of, like, what about more general shapes? Like, I know that area is a thing that exists, but I've never really thought critically about like what the definition of area should be. And in this video, we're going to try to probe into that a little bit. So we're going to take a shape, namely the region below a curve and above the x-axis, and we're going to try to approximate the area of that using rectangles. And so along the way, I'll introduce some notation. So the shape that I want to practice with is going to be y equals 9 minus x squared. Sort of a nice simple shape to work with. I'll show you a graph of that here. And if I first want to ask myself, what's the area, say, from the region like above the x-axis from 0 to, well, 0 to 0, that'd just be nothing, but say 0 to 3. So we're like tracing out and heading down and meeting the x-axis from 0 to 3, and we're going to try to approximate that region there. And the simplest thing that I could do is maybe just look at a rectangle. So I could take the y value at the point x equals 0, and that's going to have height equals to 9. And so I could take a rectangle of width 3 and height 9. And so then I could say that my first approximation to the area might be 27. And I'll show you a picture of this with one rectangle right there. But you know that's not a very good approximation, so how can you do better? Well, what you then might try to do is you might split up this interval from 0 to 3 in half. And you might then get two rectangles. So you might have one rectangle with height 9 and base 0 to 1/2, and a second rectangle whose height would then be the y value for plugging in 1.5, and whose width would still be 1.5. And I'll show you that approximation with two rectangles there. And so what's the area of that? We can give you a formula for it. So that, I'm going to call it L2, and I'll explain that notation later. It basically means left-hand endpoints in two rectangles. And so what that's going to be is 1.5 times, let's say y equals f of x, times f of 0, that's equal to 9, and then plus base times height, 1.5 times f of 1.5, and that's the area of the two rectangles. So then I could divide this into thirds if I wanted, and take three rectangles and continue the pattern. Actually, I'll show you that right there. And so how can we figure that out? Here I'm going to introduce some notation for you. So what I'm doing is I'm partitioning this interval from 0 to 3 into, well, 3 rectangles, 3 equal parts, n rectangles, n equal parts. So what I'm going to do is I'm going to say, like, suppose more generally that I had x going from A to B, and I wanted to break up that length into n equal parts. I just look at the length, which is B minus A, and divide it by the number of rectangles that I wanted. That you're going to call delta x. And so in case n equals 3, I just have 3 minus 0 over 3 equals 1. So I'd have delta x, which in this case would be equal to 1. Left-hand endpoints, say more about that in a second, and 3 rectangles. It's not delta 3, it's delta x. So that would be equal to 1, and then I'd have f of 0 plus f of 1 plus f of 2. Remember, f is equal to 9 minus x squared, so I'm getting 9, and then 9 minus 1 squared is 8. 9 minus 2 squared, that's 9 minus 4, that would be 5. So this would actually be 1 times 9 plus 8 plus 5. That would be the area, approximate area under the curve using 3 intervals. So what do I mean when I keep saying left endpoints? Well, if you're splitting up this interval from 0 to 3 into 3 pieces, then you've got 3 intervals. And each interval has a left endpoint and a right endpoint. First interval goes from 0 to 1. Its left endpoint is 0. Second interval goes from 1 to 2. Its left endpoint is 1. The third interval goes from 2 to 3. Its left endpoint is equal to 2. So when you take the y value, like f of 0, for instance, corresponding to that left endpoint, that's determining for you the height of the rectangle that you're using. So we say we're using left endpoints in 3 rectangles to get this formula that I've pictured there. You could also use 4 rectangles. There it is. And you're getting closer to the actual area. You could also use 20 rectangles. There's a picture of that. And finally, I'll show you a picture with 100 rectangles. There we go. And now you're starting to see that the approximation is getting to look pretty close to the actual area. It begins to be a little bit more difficult for your eyes to tell the difference there. And it would be very difficult to calculate out the actual approximate area there by hand, although you could do it with a computer pretty quickly. So what I can do now, let's take the picture away, and what I can do now is, say you had like L100, like I was pictured there, like 100 rectangles. How could I find a formula for that? Like, how could I find a formula that I can plug into that actually gives me the approximate area? Well, remember, n is our number of rectangles. I showed you n equals 1, 2, 3, 4, 20, and 100. So generally speaking, the delta x, the base of our triangle, it's always equal to b minus a over n. I'll draw a schematic picture of a small part of the function, and maybe we label the points of our, maybe we label the endpoints of our subintervals. Maybe you label them like x0 equals a, and then x1, then x2, all the way up to xn equals b. And x1 would be the right-hand endpoint of your first interval. The length would be delta x. Delta x is always the common distance to all of them. So if you take like the ith interval going from xi to xi plus 1, then your width is always delta x, and your height, here's your height. And so that's kind of like a picture, and the area of that rectangle is going to be base delta x times height, f of xi. And so in my example over here, for L2, x0 was 0 and x1 was 1.5. For 3 rectangles, x0 was 0, x1 was 1, x2 was equal to 2. It just happened to work out evenly. In general, the formula for the ith point is going to be, well, start with x0. And if you're moving out through I intervals, each one having length delta x, then for x1, you'd just be adding, delta x to it. But for xi, you have to add delta x I times to get all the way out to the ith interval. So you end up with this formula, and x0 is equal to a that's given to you in the problem, usually delta x b minus a over n. You can figure that out. And then you can figure out x sub I, which is x0 plus I times delta x. So finally, you can write out a big formula. Here it is for left-hand endpoints with n rectangles. And that's going to be delta x, it's b minus a over n, times f of x0 plus f of x1. You continue on until you get to the left-hand endpoint of the nth interval, which is going to occur at x sub n minus 1, because it's the left-hand endpoint of the nth interval. And so that's the formula. When n is equal to 100, then you get 100 rectangles with the same width. So that's how you would find that out. If you actually wanted to calculate it, you'd have to use this formula to plug in for each individual, like x sub I. And that would give you the answer. So that's how we approximate the area under the curve using rectangles. There's a little bit of notation, there's a little bit of formality, but the idea is quite clear. You specify how many rectangles you want to use, you specify how fine you want the approximation to be, you divide up or partition your interval from a to b into n equal subintervals of width delta x, and the formula is length over n for delta x. Then you find a formula for the endpoints of those intervals, which you can get by just taking your first left-hand endpoint a and successively adding the width to get the successive endpoint. Plug those into the function to get your y values, multiply by delta x, then that's giving you the length or base times height formula for each of your n rectangles. Add that all up together. That's called the left-hand endpoint approximation to the area under the curve.